Oh, okay, and there it is. All right. So if you'll recall from a few weeks ago when I started presenting on the unit complex disk under the Poincare metric, this is the set we're working in. It's just the interior of the unit disk equipped with this hyperbolic metric. And I made a couple of claims um, at the very beginning before moving into talking about the Schwartz lemma and then Schwartz-Pick lemma. I made a claim that the Gaussian curvature of this space is -1 everywhere, and a claim about the shape of geodesics, that geodesics are diameters of the disk or circular arcs that meet the boundary at a right angle. And we're going to examine those two claims explicitly today. So the formula we're going to be using for Gaussian curvature is this: curvature is equal to negative Laplacian of the log of our conformal factor in our metric divided by the square of the conformal factor. So this conformal factor, lambda z in a metric, describes how a geometric space is locally stretched or scaled relative to a flat metric. So if we're doing just the Euclidean metric, then this lambda z squared here would be just 1. And you can see that this would work out log of 1 is just going to be 0. We would get a curvature of 0, as we would expect in a flat metric. And so in our hyperbolic metric that we're using, our lambda z is just going to be whatever is multiplying modulus dz here. So this is 2 over 1 minus modulus c squared. And this relates how the space is stretched or scaled, as I said, compared to flat Euclidean space. So if we examine this at the origin, we'll see that if we were to drop a tiny Euclidean ruler right at the origin would be of length L, would be a tiny step right at the origin is twice its Euclidean length. And then as we approach the boundary, this quantity on the bottom here goes to 0. And so our conformal factor goes to infinity as we approach the boundary. And so we'll start by taking the log of our conformal factor here. And then the Laplacian, which is this right here, this partial derivative with respect to both z and z conjugate. And so Laplacian of the log turns out to be 4 over 1 minus modulus z squared. And that is, in fact, the same as the square of the conformal factor in this case. So we just get negative conformal factor over itself, -1. Any questions about the calculation that produced the curvature? All right. So then the other claim I made is that geodesics in D are straight lines through the origin and circular arcs intersecting the boundary at right angles. And we will use calculus of variations to minimize the arc length functional governed by the conformal factor. So here is our arc length functional. What this is if we have a smooth curve, z of t, with t in some real closed interval, a to b, then here is our conformal factor. Or I'm sorry, this is our arc length functional, and we want to minimize this. And we can actually, by the way, because we're not necessarily all used to seeing this z dot, this is Newton notation derivative with respect to t. And so we can simplify this calculation. We're first going to just consider a geodesic passing through the origin and a point on the positive real axis, 0 to some x1 in R, with x1 between 0 and 1. And so we parameterize any arbitrary path between these 2 points as z of x as x plus iy of x. We'll have y of 0 equal to 0 and y of x1 equal to 0. So we're working with any arbitrary path in this, any arbitrary smooth path in the disk that connects the origin to a point on the positive real axis. And now our arc length functional looks like this. We just have a fraction with 2 times the square root of 1 plus y prime squared, where y is a function of x, over 1 minus x squared minus y squared. And our objective here is to minimize this integral in order to produce a geodesic. And we note that the integrand for any value of x is minimized if y prime is equal to 0 and if y is equal to 0. Because if y is not equal to 0, then the denominator decreases. If y prime is not equal to 0, the numerator increases. So this integral is minimized when our path is in fact a straight Euclidean line segment along the real diameter of the disk. And so now, for the general case of all geodesics, we're going to apply our Mobius transformations of the disk that we talked about a few weeks ago, I think. So once again, this is the form of our Mobius transformations of the disk. This particular transformation for any Z naught that's in the disk maps. Z naught will go to 0 and 0 will map to negative Z naught. And so first of all, if we set Z naught equal to 0, then this is just e to the I theta z. So this is just a rotation of the disk. So now we've shown previously that the real axis, the diameter that forms the real axis along the real axis in the disk is a geodesic. So any rotation of the disk will rotate that diameter. So all of the diameters of the disk are geodesics. Second, Another fact we know about Mobius transformation is they map straight lines and circular arcs to other straight lines and circular arcs. So if I have a straight line under a Mobius transformation, that can become either another straight line or a circular arc. If I have a circular arc under a Mobius transformation, that can become either a straight line or circular arc. And finally, the third thing we know that all of our transformations are straight lines or circular arcs, or all of our geodesics must be straight lines or circular arcs now. The third thing we know is that Mobius transformations preserve angles and diameters that we've already proven are geodesics always meet the boundary at a right angle at both ends. So all of the geodesics have to meet the boundary at right angles. So we can conclude that geodesics in the disk are along diameters or circular arcs meeting the boundary at a right angle. This is what they look like. Any questions about that? Okay, I think that concludes what I had prepared, actually. Two short confirmations of things about claims I made about the disk.
So just a few comments regarding the next presentations regarding what we are working on. So one is in terms of the generalization, the other is in terms of the mathematical tools to develop together in the research. So it might be good at this point to think now we have a decent amount of understanding on the one-dimensional unit disk in C1 that we prefer to call by the hyperbolic space. In this case, so-called the real hyperbolic space and complex hyperbolic space are coincide, they're the same.
Right.
When it comes to generalized to the higher dimensional hyperbolic space, those are no longer the same. So
Right.
complex hyperbolic space and real hyperbolic space are different. So real hyperbolic space stands for the complete simply connected Riemannian manifold whose sectional curvature is negative constant everywhere, whereas complex hyperbolic space is one model is the also unit ball in Cn that has a not constant sectional curvature but constant negative holomorphic sectional curvature. It's a different concept. So what we look at here can be generalized to the any higher dimensional unit disk in Cn. For some possible extension, could be even for the infinite dimensional hyperbolic space, choice before. So it's good to study with the Riemannian geometry language to understand any dimensional complex hyperbolic space and what this Church lemma really like the man from that like the higher dimensional perspective. That's one thing which is already well studied. It's just a matter of studied together, and I expect that you might drill some of those pieces in coming fall and try to present accordingly with also learning the necessary language of the studying complex hyperbolic space. That's one thing. Another part is, so as we said, so we will develop how to like the define the new classes of the negatively curved complex spaces with the Schwarz lemma so that we should be able to extend some classes via the tools of in the probabilistic like the ways. So this is what I am aiming for doing the research for your dissertation. So it takes time, but definitely we are able to do it. And our like the starting point, the foundation is what you already like to study. So this is very well done in terms of the geometric structure and the necessary details, including what Take already presented in terms of the probabilistic tools that we already saw. Yeah, so this is awesome. So if there are no other comments or questions, then we will move on to the next presentation.
And I share my screen. Yeah. Is it good or not? Hello, my name is Hejin, and today is my first presentation. So I prepared my hand calculation on the Fisher information geometry of the one-dimensional real number family. So as you know, the probability density function of a one-dimensional number distribution is parameterized by the mean mu and the standard deviation sigma, and where mu is real and sigma is positive. So the parameter space is upper half plane. So I don't know about the hyperbolic space as well, but the goal is to show that the Fisher information metric on this number family is closely related to the Poincare upper half plane metric. So so I want to show my calculation today. And so sorry for not related about first page, but yes, I will introduce the definition of Fisher information metric on this slide. The first, let standard manifold M like this, and in the case of normal distributions, the zeta equals mu comma sigma, and the L zeta x is be the log likelihood, and the Fisher information metric is defined by Gij zeta. In words, that this is the expected product of the score functions. In information geometry, we interpret this Fisher information metric as the coordinate represent of Riemannian metric tensor. So I don't know about about tensor, but yeah, in the fact that, and that is Gij zeta is information geometry. So the next is explain about the definition of KL divergence. Let Px zeta be the first density and Px xi is second density. The KL divergence P bar Q equals like this in the continuous continuous probability distributions. So I computed Taylor expansion in a first derivative and second derivative. The first derivative compute like this. So in derivative by xi I, then we can easily see that there's no xi in these terms, so it becomes 0 and comes out the minus log p x xi out of these terms, and remove these terms, and it becomes like this one. And we already know that probability density, the integration of probability density is equals 1, so that is constant. So derivative xi I, then we can compute like this 0, and second derivative like this. We derivative by xi I and xi j, then we can compute like this. And the thing first I uncomfortable at the first computation is this one, because it I don't know about the exponential -2, but yeah, sorry, my mathematical words is not good yet, so I will try next time. But exponential -2 is divided by -1 and -1. So this one comes out, and we already know the upside. So it becomes 0, and -1 and -1 distributed by each terms. So we can see like this. So already we saw about the feature information metric definition. So it's similar to these results. So we can observe that is similar to feature information metric and KL divergence, the second derivative of KL divergence. So we can define I under IZ, define like expectation of zeta and these terms. Oh, so this is my calculation of one-dimensional KL divergence between two Gaussian density function, and here's my computation like this. So this is the formula of KL divergence, and I input the two Gaussian density function of each terms like P and Q. So P I denoted like mu0 and sigma0, and Q is mu1 and sigma1. So we already know that log likelihood px over qx. So I computed like log ratio like this. So input this log ratio to these terms, and I have to compute these terms. And the second term is easily, as you know, that is sigma 0 times 2. Times 2? No, times 2. What is the, what can I call that? Not times 2. What is this? Professor Joe?
You can call whatever you'd like to call it. It doesn't matter.
Okay. Yeah, exposure 2. And the sigma 0 is difficult. So compute this, then I can compute like -1 over 2. And we try on these terms, the first thing. And this term is x minus mu1, and p0 x is the point of this calculation. Because p0 related to mu0 and sigma0, so there's no terms of the mu0. So we want to see the x minus mu0 of these terms, so made it and remove it and minus mu1. So x minus mu1 to exponential 2. So we derived like this and input. Then, oh, sorry, there is cut. And yeah, we can easily out these terms, and the constant comes out, and the result of first term is like this. So we want to see the KL divergence or in the view of Taylor expansion. So fixed mu 0 and sigma 0, because we want to see the mu 1 and sigma 1 is how far from mu 0 and sigma 0. So I call this term the KL divergence function as f, the capital F, and f mu 1 comma sigma 1 becomes like this. So we can partially derivative in by mu 1, then the result like this, and the second derivative by mu 1, then sigma 1 over sigma 2 and the mu 1 and sigma 1, then we can obtain like this. And as you know, the continuous function and this function is smooth, and we can derivative in infinity. So infinitely, so equals sigma 1 and mu 1. And the last thing is sigma 1 2 times partially derivative to f, then we can obtain these terms. At the first point, I already mentioned that we fixed mu 0 and sigma 0. So we want to see that mu 1 and sigma 1 is how far from these terms. So we input this m1 as mu 0 and sigma 1 as sigma 0. Sigma 0. So I wrote the matrix like this, but it yeah. Then mu 0 and sigma 0, then input, we can obtain the sigma 0's 1 over sigma 0 2 and 0 0 2 over sigma 0 2. So we call this matrix as Fisher information matrix, and it is same as G equals 1 over sigma 0 d mu tensor product d mu plus 2 d sigma tensor product d sigma. So some of you guys already know that it is similar to alpha half plane, but it's different. That thing is sigma coefficient, that is 2. So we call that almost upper half plane. Yeah. So I wrote this upper half plane hyperbolic metric, the definition of this, and G under H is equals 1 over Y 2 and dx tensor product dx plus dy tensor product dy. We only scaling these terms like sigma. And if you want to view the space under hyperbolic metric, then you can transformation that the coordinates like tilde mu equals square root 2 mu, and d tilde mu equals sigma 2 mu d mu. And so we can transform like this and transform again. Then it equivalent to G Fisher information metric equals 2G hyperbolic metric. So what I observed this computation is the Fisher information metric is the scaling the hyperbolic metric, and the constant times scaling that like 2 is the curvature is becomes like descent. Okay. Pass. And so we can compute to see this curvature, how becomes curvature. Then we can compute Gaussian curvature like this. And yeah, v 2v xy, and these of calculation, then I obtained 1 over y 2 and the Gaussian curvature formula like this. And I input the result of the calculations, and I obtained minus 1 over 2. So we obtain a negative Gaussian curvature. So yeah, my presentation is finished. Then if you have a question, then
Yeah, thank you very much for the preparation of the seminar and also contributing the important topic. So participants can see, so up to here, there are two presentations today, but we are in fact talking about the same geometric structure, and the hopefully you can see the scaling factor here. I mean, talking about the two. So compared to the your like the scaling factor 4, how that really affects, as has been pointed out, scaling determines the curvature. In the case of the 4 in numerator, that determines the Gaussian curvature to be -1. Now we take the 1/2, so that's why curvature now becomes -1/2. So it is super natural. So I wanna point it out. So the space of the probability distributions, so equipped with the Fisher information metric coming from the KL divergence, this field, this territory is usually called by information geometry, that I'd like to develop both of the disciplines of the not applied math only, but also in the direction of the pure mathematics, with the collaboration with Professor Cheng here. So this is a interesting like topic to develop by all means. So I also want to point out, so it really matters to drill this computation in depth. So I first want participants to point out the computational detail. There are some like the missing gaps and some technicality details, at least in the PhD level of mathematics. People should recognize what are the gaps that we are relying on in terms of measure theory, for example, and what's the important like the techniques of this computation, those kind of elementary details I'd like to discuss. So I first want to let participants here to point out some calculational details. So in terms of what we need to drill, what we need to understand, what are the kind of the supportive statements that we rely on to carry out this computation. So any thoughts or comments? Well, let me then do one by one. So, Hajan, if you go back to on your note, the very first second page, the definition of the Fisher information matrix, I want you to realize. So, in the definition, G sub ij theta. So, this is just a nothing but the integration with the Gaussian density. Gaussian density. So our reality is just nothing but the moment computation of the Gaussian density. That's first thing. So as long as you know how to handle the moment computation with the Gaussian density, all those are sort of the consequences from that computation. Then what's the importance of the like the spirit of the moment computation of the Gaussian density is the uh, basically change a variable to derive the so-called the gamma function. So this is important, like the detail. So as long as you know how to handle change of variables with the gamma function, starting from the Gaussian density, then actually you are able to reproduce our computation here. And even in the definition level of the KL divergence, still the same. So if you just fix this P to be the Gaussian density, same spirit. So log of something is just nothing but sort of the like the moment with the following reason. So in this one variable computation, so we know how to handle, how to take the derivative, we know how to take the antiderivative and so on. And if we do not know how to do the computation, so also one of the important spirit from this page two is because if you have no idea, we should take Taylor expansion. So it is important. So Taylor expansion is a local expansion that makes everything works out. So for example, it is important to know get the sense of how to take the Taylor expansion in your own way. So it is important to memorize the so-called Maclaurin series of the e to the x, sine x, cosine x. So e to the x is can be represented as a summation from 0 to infinity k factorial to the x to the k over k factorial, for example, and you are also able to represent cosine x, sine x in a similar way. And I also want to point it out that this like the log matters. So usually the college students, so when they take the final, probably most of them, so with the good like the decent like the grade, know the Maclaurin series expansion of the sine, cosine, and e to the x. I know they know them both, but ln also matters. So please memorize the expression of the ln 1 plus x. This is written as, so it starts from not the constant, start from the x to the order of 1. So it is expanded as x minus x squared over 2 plus x cubed over 3 minus x to the power of 4 over 4 without the factorial. So memorize this form. So even we do not know how to handle ln of something, still we are able to take the Taylor expansion. So as you remember the Taylor expansion expression of the ln 1 plus x, then you can apply to the ln x because ln x is same as ln 1 plus x minus 1. So over there, you are able to take the Taylor expansion. Then each Taylor expansion just gives the, again, moment computation with the Gaussian density. So anyhow, you are always able to compute this up by yourself. So you should like to get this spirit that this is like the Fisher information metric. Of course, from your like the way to derive, we already know how they are related between the Fisher information metric and KL divergence. But I want to point it out. These are just nothing but the moment computation of the Gaussian density. So that's so important. And by using the Taylor expansion, all you just did is Taylor expansion, which is the foundational key. So that once you reduce the computation to the moment computation of Gaussian density, then then you just need to look at the gamma function from the change of variable, and that's it. You know how to handle everything. So that's why moment computation is so important. So in terms of computation, so before I move on to the next, like the important like the part to practice, so I wanna put emphasis how important to get the sense of like the understanding the way to reduce the computation before you write down with the note. I want to point it out that you should see the clear structure, how you are able to reduce the computation. So without writing anything. So that from this page, there are two spirits. One is the Taylor expansion. The others, once you know how to do the Taylor expansion, then it's just a matter of doing the moment computation of the Gaussian density. That's it. So and others are just putting the name in different like the context, but the mathematically speaking, it's just all I said. So that's important to understand what I'm talking about in your own way, so that as long as this clicks in your like the mind, then you are always able to produce the computation in your as you wish, because we all understand the reality. That's one thing I want to point it out. Then now if we go to the next page, page three. Yeah, here. So including the PhD students here. So via the measure theory perspective, what is the mathematical gap that we should concern? in this computation?
I think changing order derivative integral.
Yep, that must be considered for the math major. Of course, Hagen's direction is not aiming for becoming mathematician. Her like the disciplines is for the engineer equipped with the hardcore mathematics, but it is important to recognize the like the rigorous like the step that when we flip the order of the differentiation and the integration, this is not free in general. So in general, this might get failed. So if we flip the order of the integration and then differentiation, we need to be careful. And this is the part that when you like write your own paper to claim that from this like the derivation, we abstractize, generalize this like the framework in terms of this algorithm, then mathematical assumption should be made in a sense that we are only restricting the class of the probability densities, for example, that we are able to flip this like the order. This is not free. So there should be the cases that they might be failed. That's the place that in the paper you need to put certain assumption. So why we need to put this assumption then? So if this like the flipping the order fails, then we might not be able to get to what we desire to get. So this is also the one of the key motivation to study mathematics to understand these types of the like the perspective. And other than that, I love our computation. And before I move on to the very like the last like the part of the practicing, I wanna encourage the very first like the year of the PhD students because I also experienced the same thing. So when I first did the TA at University of Connecticut, I was completely overwhelmed because I never been to United States. I never did the TA for myself, and I was worrying about my language, like the expressions and the way to explain what I prepare, all those kind of things. I completely feel awkward compared to just explain everything in Korean. I kind of like has the lack of the confidence and so on. The way to overcome is just to get revered as much as possible. Then at some point we don't give a shit that much. So even we make the mistake in terms of grammar, we kind of forget about the term that we'd like to use. It's kind of okay because nobody give a shit. So just revere as much as possible, then you kind of feel, ah, I'm okay. So that's kind of the spirit. So even so, you might want to get corrected everything as you wish, but it takes time. So try to just do whatever you want. So as long as people are understanding what you're talking about, then that's enough. It's just for the communication. That, but still, one need to be brave about. We never experienced before. I know this is kind of like a difficult, but this is good to like present this way so that you might not forget later on compared to just a study all by yourself. So so I still want to point out one last like the mathematical like the part to realize. So up to here, or the computation details are just nothing but taking derivative. Now we have a differentiation and integration is calculus. It's a one variable calculus, right? Calculus. But if you now go to the page 5 to 6, you can realize, yeah, you can just go one more page, just between page 5 and page 6. Yeah, like this. I want you to realize it became linear algebra. So all you did was just a one variable differentiation, one variable integration, but it naturally turned out to be the 2 by 2 matrix so that it also became to usage of the linear algebra. And so by the way, one correction, this because this term is important, we are not putting this as a almost. So this is still upright to plane hyperbolic metric. It's the same. It's up to the like the either the basis change or the coordinate change. The metric or the first fundamental formula Riemannian metric does not depend on the like the choices selection of the coordinate, local coordinate. So this is not almost, it's just the same. But as you now see, this form is completely different from what we desire to get. So that's the concern. And by using the coordinate change, you just obtain the desired form. That's exactly what one should do. But this is also part of the definition of the so-called Riemannian manifold. So that's why we need to learn those like the language. But or what you did is completely like awesome. And I want to just get the structure understanding that linear algebra is not separate from doing calculus. They are naturally overlapped. So even those data are coming from the integration and differentiation, but from there we are able to making the linear algebraic structure. Then we at some point use the linear algebraic computations. So that's why at some point one need to put the effort to make the sort of getting the sort of the harmony of doing. So what I'm really doing is the, for example, calculus detail, but you can kind of see the like the structure from linear algebra and vice versa. And from there, so for example, like this is very good understanding. So the matrix form is not like what we were aiming to get, but still from there, some mathematical like the theory works to make it to be happen. So from there, you might not forget. So that's the way to learn something. So all participants of this seminar is just required to just conduct the elementary, but not trivial. Any of the computation today is not trivial at all. So, but those are elementary. So just conduct the computations and try to put the meaning of it in your own way. Just one like the point I want to make is that in the PhD level study, so because each of you have a specific disciplines after all, and even we might feel like the pressure to catch out the knowledge that we feel we need to know, but it actually doesn't matter. Doesn't matter. So as long as you know how to drive the values by yourself, or rest of it are just putting some interpretation. Even some of the interpretation should be super useful. That's correct. But after all, we need to put new meaning from the context. For example, even today's like the two different like the presentation. One is based on complex analysis. Another one is based on the integration of the Gaussian density. So context seems completely different. One is complex analysis, the other is more like the statistical and probabilistic point of view. But now we see they're actually they're talking the actually same geometric structure. So the interpretation could be different, and even tools could be different. Doesn't matter. So interpretation from the previous, like the literatures, might not be that much matter eventually. So, but it matters to conduct this computation all by ourselves. So once we get the sense of why we need to just replace this matrix by the another matrix, something else, then so from there we should learn something. So some like a theoretic like understanding should like the naturally enter into understanding the material properly. But we do not need to catch up every like the knowledge that's not required. So yeah, I want all of the participants to just present as Hasin did today, and it just takes time to get like the mature enough to produce something really brand new. But this is like the spirit of the doing like a PhD level like the training. So just conduct the elementary computations as quantity as possible. And then, so from each of us context, just put new like the interpretation. And from there, you might be able to formulate new like the statement. And from the computation, you have some supportive evidence. And then that's it. So that's what we are aiming for doing. And for couple of weeks from this point, so because I want PhD level students to get focused on the passing the qualifying exams that you guys are preparing. For a moment, I wanna just conduct the seminar with the specialization of the information geometry with the like a PhD level scholars for a moment, but just a temporary. I will eventually just resume our like a seminar, and all of the participants are welcome to join. But it's more like the indeed research oriented because these scholars need basically papers. So we will just conduct a launch like a project just immediately or together, but it's not the learning seminar for a moment. So any of you can join, but it's not mandatory for a moment until probably the first week of the August, right? And the first week of the August is for the qualifying exam period. So
Right. The 3rd, 5th, and 7th are our qualifying exam dates.
yeah, sounds good. Uh, all right. So before we finish the seminar, including the comments and questions to Hajin, any comments or questions? So, and there was, I said there would be a third, like the presentation, but I'd like to do that with the specialization of the number theory later on. So we will do the third presentation, not today, but next time. So any comments or questions?
I have a question about some general idea, generalizing this calculation for about beyond the KL divergence. It has a meaningful meaning for computing the first and second derivative of, for example, Bregman divergence or something other divergence. It, I think that it would be applied to for example, the definition of differential privacy because it restricts some divergence between two random variables. So this calculation could be extended to such things.
I completely agree. So even in the level, so for example, if we go back to the page 2, so Haejun, can you go back to the page 2? So we rely on the expression of KL divergence indeed a lot. And so I am against the non-literature's explanation in a sense that, so let's just look at the KL divergence. Even this is not distance, but this is super important without justifying in the mathematical way. So this like the even expression should be justified it with each of the different like the context. So what Hejin today justify is in the Taylor expansion. After all, what we got is the efficient information metric. So it's kind of okay. So, but I don't think this is just half of the justification. It doesn't mean that this justifies to like the use it. So why this could be super useful rather than this tail expansion. The second like the order gives the official information metric. So and even we know the explicit form of the K divergence with Gaussian densities as has been also like the computed today. So unclear. So one like the context I am thinking is so in the like the differential privacy context. After all, this is to compare two densities basically compares two densities. But the point is, this is not distance. But when it comes to talking about the preservation something, then I basically expect there should be the topological structure. So it seems like even this is not metric topology, directly speaking, but still there is a topological structure that should be preserved via the expression of a KL divergence. So that what I expect is this is outside of metric, like the topological space, but still it brings the natural like the topological structure, then that should be able to compute something out. So eventually we want to compute the like the privacy, like the quantitative and qualitative like the way, but the expression so far seems like a kind of heuristic. So there should be the mathematical framework to unify and justify why we should rely on this expression and more on like the including like the EM algorithms, for example. So it uses this in a very significant way, but it is unclear because in information geometry, we know we can also generalize this so-called the alpha divergence, and also alpha divergence is not the end of the classes that one can consider. So Bregman divergence is now like a known as a quite like a helpful and like a useful like the objects in statistics, but I actually do not really like to see how to mathematically understand it. So from probably Dr. Kim's presentation, maybe we might see more like the topological meaning out of it. So yeah, let's try to look at it.
I see. Thank you.
Yeah, any other comments or questions?
Yeah. Then I stop the share screen. And thank you
All right,
for
then
everyone.
we might just end the seminar today relatively early. And from next week, we will focus on more information geometry side. And for Dr. Children's presentation regarding isogeny graph, I'd like to connect them with the machine learning project within our like the communities. And for that, we should like to make more conversation. So I will finish the record here. And thank you very much all for contributing this seminar. I'll stop the record.